In this video, we are going to be observing the properties of amines. Understand that the nitrogen atom in typical amines is sp3 hybridized. And as you can see in the structure given in the following slide, we have an amine, this is specifically trimethylamine. The nitrogen atom is bonded to 3 alkyl groups and a lone pair. This is the typical bonding pattern for a nitrogen atom. Now, we know that tetrahedral molecules have bond angles that are around 109.5. And as we look at the bond angles around the nitrogen atom, they are actually 108 degrees. The carbon-nitrogen bond, we know that they have a length of 147 picometer, which is slightly shorter than carbon-carbon single bonds and longer than carbon-oxygen bonds. Now, understand that there are some circumstances in which the nitrogen atom, instead of being sp3, is going to be sp2 hybridized. Now, when it comes to this, we understand that the nitrogen atom with 3 alkyl groups are actually chiral. And I know that this can come up as a surprise because for the most part, when we think of chiral atoms, we think of a carbon atom having 4 different groups. But in the case of a nitrogen, the reason why we say that that nitrogen atom has 4 different groups is because the lone pair will count as a group. Now, amines generally are not topically active. As you can see here from the image that we have in the bottom of the slide, this is just talking about a nitrogen atom that has 3 different R groups, and we can see its mirror image on the other side. Now, understand that what happens overall in why these amines may have at some instance some sp2 character is because what happens is that the nitrogen undergoes a pyramidal conversion that occurs very rapidly. As you can see here from the energy diagram that we have in the following slide, we have the 2 different mirror images that are present for amine molecules. As we have the reaction coordinate, what we can see is that there is an intermediate that is formed that is actually trigonoplanar. Now, understand that this is higher in energy than both of the different enantiomers that we can have for an amine, and since it's higher in energy, it actually rapidly converts to the other conformation of the amine. Understand that amines with fewer than 5 carbon atoms are typically soluble in water. When it comes to the attractive forces or intermolecular forces between amines that are primary or secondary, that means the attractive forces within themselves. Understand that primary and secondary amines, because they can have an intramolecular hydrogen bond, they have higher boiling points than the ones that can happen between tertiary amines. So if we compare the boiling points of a primary amine to a secondary amine to a tertiary amine, we see that the primary amine has a higher boiling point. And again, it comes from the attractive forces, the hydrogen bonding events that are occurring. What happens at the level of the tertiary amine is that specifically, you can understand that since the hydrogen atom is not bonded to the nitrogen, it is actually bonded to the carbon atom. And I'm just going to draw out one of those CH3s. Because the hydrogen is bonded to a carbon, a tertiary amine cannot have hydrogen bonding events to itself. It actually has dipole-dipole events. You may remember from general chemistry that when it comes to intermolecular forces, the higher number and the strength of intermolecular forces actually has some effects in boiling point. And as you can see, that's what we see the trend when we compare primary to secondary to tertiary. Now, many small molar mass amines have unpleasant odors and they smell like rotten fish. Here we have two different examples just illustrating amines that are small molar mass and they will not be pleasant to smell. Now, when it comes into the basicity of amines, understand that they are stronger bases than alcohols and ethers. So, amines can actually be readily protonated by strong and weak acids. As you can see in the example that we have here for the equation, here we have triethylamine in the presence of a carboxylic acid. This is ethanoic acid. And when these two molecules are in the presence of each other, as you can see, the protonated amine is going to have a higher pKa than the one of the carboxylic acid. So this reaction is actually favored towards the deprotonation. So understand that it is useful to have a general idea of the pKa values of protonated amines. They tend to be between 9 and 10. As you can see in table 22.1 in the textbook, we have the pKa values of the ammonium ions of several amines. It is a good idea to know it, but as you can see when you look at the ranges, is specifically here between high 9s and low 10s. That's why I just threw the general number there between 9, 10. Some people consider it between 9 and 11. And this is just the rest of the molecule. This is a little bit different because if you look at these amines that are heterocyclic amine or aryl amines, the pKa are actually lower when they get protonated, so they are going to be slightly more acidic than the ones presented in the previous slide. So as I mentioned previously, in general, amines with more than 5 carbon atoms are only slightly soluble in water. And the reason is because the more carbon atoms you may have in an amine, even though through the nitrogen atom, amines can do hydrogen bonding with water, once you increase the nonpolar character of having those carbon atoms, that's where the solubility decreases, okay? Solubility, as you can see, is enhanced by the presence of an aqueous acid, but that comes from the idea that we can have deprotonation of our aqueous acid, and amines can be extracted from organic impurities using aqueous acid because what we're going to convert them is into an ammonium ion, and typically the product of the reaction is an ammonium salt. The pKa of most alkylamines, conjugate acids, are between 10 and 11, as I expressed previously. Now, arylamines are less basic than alkylamines because the lone pair is delocalized. So as you can see here, specifically, we have the molecule of aniline. And we can see the 3 different resonance structures that are available for the molecule of aniline. What this is representing in the bottom of the slide is the delocalization of the lone pair. So that means that nitrogen, for example, in aniline is going to be less available for protonation. Understand that in the molecule of aniline, the presence of electron withdrawing group also decreases its basicity. So as you can see in the molecule, we have aniline in the middle. We have an electron donating group by having that methoxide group. Okay, and here we have a cyano group, and as you can see, the electron withdrawing group, once we are going to have a protonated on the nitrogen in the aniline, you can see that the pKa became really low, while you have an electron donating group, then the pKa is around 5.3. So that's the difference between them. Understand that the lone pair of an amide is not considered to be basic or nucleophilic because it is actually extensively delocalized into the carbonyl group. So when we look at the carbon nitrogen bond, which is right here, this nitrogen carbon bond is actually considered sp2. So it has an sp2 character. Because of the resonance structure that we have specifically at the amide or of the amide. Lastly, at physiological pH, meaning 7.3, amines exist primarily as an ammonium ion. So understand that if an amine is under those conditions, they are going to be protonated, forming an ammonium ion. So this comes from the idea of the Henderson Hasselback equation. Remember that is the buffer equation. And it can actually be utilized to calculate the ratio of amine and ammonium ion at a given pH, but understand that you will not be tested doing those calculations specifically for amines.